From the Library of Congress in Washington, D.C.
Good afternoon. Welcome to the National Book Festival. My name is Peter Rudik. I'm Director of Legal Research at the Law Library of Congress, the largest collection of legal texts and institution which responds on all and deals with all issues related to global laws. That's why I think it was the thought of organizers of this festival when they asked me to introduce Professor Halpern, because his book, Einstein's Dice and Schrodinger's Cat, deals also with laws of the universe. Yes, and I think it's not also a coincidence that this book is much broader than just a story of major discoveries in physics made in the middle of the 20th century. It covers a myriad of personal and social issues. And it does so because if you will go to the website of the University of Science in Philadelphia, you will see that Mr. Halpern is mentioned there as a professor of physics and fellow in humanities. He is a scholar who published 13 scholarly and popular science books. He participates in radio shows and looks for science on The Simpsons. Professor Halpern will sign his book starting at 5:30, and if you don't have a copy of his book yet, you can buy it downstairs at the book sales area. Please enjoy conversation with Paul Halpern.
Thank you very much for that kind introduction. I'm absolutely delighted to be here at the National Book Festival for my first time here. And it's really a special time because it's the 200th anniversary of Jefferson's fantastic contribution to the Library of Congress. I'm going to be talking about my new book, Einstein's Dice and Schrodinger's Cat. And this year is a very special year for Einstein. This is a remarkable year to celebrate the great genius. First of all, it's the 100th anniversary of his masterful theory, the general theory of relativity, which is a theory of gravitation that surpassed Newton, superseded Newton, in describing how the universe develops over time. It's an amazing theory, mathematically very beautiful. It's also the 110th anniversary of the predecessor theory, which is special relativity, which talks about how things move when they're moving close to the speed of light. What happens to things? Time stretches out, things expand. It's pretty remarkable what happens when things move close to light speed. Things acquire more weight. All of these ideas have been incorporated into modern science. Now, we also look at the 60th anniversary of Einstein's death. He died in 1955 in April, and we think about Einstein's legacy. And finally, we look at his work in 1935, which we're celebrating the 80th anniversary of, his work where he combated, or tried to combat, quantum randomness through his idea called the EPR experiment, which led Schrodinger to develop the cat experiment. Now, even 60 years after Einstein's death, he remains an iconic figure for genius. If you see a picture of Einstein, practically everybody recognizes who he is and thinks of him as a genius. Now, this talk is also about somebody named Erwin Schrödinger, who was also a Nobel Prize winner, but I doubt that many people recognize him for his face. People recognize him, rather, for his cat. So when we mention Schrödinger, nowadays, his cat has become an internet meme. So people think of him as a figure that's perplexing because mainly of his cat. Now, I'm not going to go in great detail into his cat experiment, but basically, it's a rather gruesome thought experiment, which has never been tried as far as I know. And it was proposed to demonstrate the absurdity of quantum physics. So he proposed this as a way that people could see how ridiculous standard orthodox quantum physics is. He imagines a cat trapped in a closed box with a radioactive sample, a Geiger counter, and a vial of poison that is triggered by the Geiger counter. The radioactive sample has a 50-50 chance of decaying within an hour. That means that the Geiger counter has a 50-50 chance of going off within an hour, the poison has a 50-50 chance of being released, and the cat has a 50-50% chance of making it for the hour. Now, according to standard orthodox quantum physics, the radioactive substance is in a mixed state called a superposition of being decayed and not decayed until it's observed. That means that until you open the box, if the box is closed, the cat is in a 50-50 state, a superposition of living and dead until the box is open, and then the cat is said to collapse into one of the two possibilities. Well, Schrodinger thought that this was ridiculous. He sent a letter to Einstein to that effect. Einstein thought it was ridiculous, but he didn't win over the quantum people. They thought, well, their theory is still sound, and that's what people think today, that quantum physics, even though it has some ridiculous elements, is still sound. Now, Schrodinger's cat has become, particularly in recent years, a symbol of ambiguity. So I happen to use Twitter a lot, and one time I posted a very solemn picture of Schrodinger's grave, and the immediate responses I got were, is he there or not? So I thought, well, people are not really taking Schrodinger very seriously these days. Now, this is an example from making fun of a Monty Python sketch, the parrot sketch, and saying that the parrot is in a mixed state of being dead or just resting. Now, interestingly enough, looking into the life of Schrodinger, it does turn out, rather, that he is a very contradictory figure. So he's a man of great contradictions. For example, he often walked into conferences or his university very casually dressed up like a backpacker. He was turned down at some conference hotels because they just thought he was, somebody from the street, not a scholarly figure, because he was wearing a backpack. And at that time, there was a very strict dress code. And yet, there are pictures of him on a beach with a blackboard and dressed up in a suit doing calculations. So he kind of did what he wanted to do. He was a man of remarkable talent. He was a Renaissance man. He spoke many languages. He grew up speaking German and English perfectly fluently and learned all these other languages. He studied both experimental and theoretical physics, but then afterwards thought, well, maybe I should just become a philosopher. And probably one of the biggest contradictions was when he lived in Ireland, which is the subject of my book. He effectively had two wives because he couldn't make up his mind there. He had his wife that he was married to, who he loved dearly, and then a woman who was the mother of his daughter, and he loved them dearly too. And so he did not see that as a contradiction. He was a student of Schopenhauer, or interested in Schopenhauer, and thought that nature sort of had its own will, and that you were drawn towards certain things, and it really wasn't up to you. It was just kind of part of the natural fabric if you kind of end up with two partners or whatever. It's just part of natural law. And he kind of went where nature took him, where fate took him. He went from place to place throughout his lifetime. Ireland was the place he stayed in the longest, but he lived in many different countries, had a very long, active life, working at different places. And the Austrian physicist Walter Thirring once described him as saying it was like he was always being chased from one problem to another by his genius, from one country to another by the political powers in the 20th century. He was a man full of contradictions. So the two characters in my book first met at a Vienna science conference in 1913. And this was the last hurrah for the Austrian-Hungarian Empire. They hosted this very lavish conference in Vienna. All these German-speaking scientists came to it. Einstein gave a talk there. Schrodinger was in the audience. Einstein spoke about his new theory of gravitation. Now, I said that this is the 100th anniversary of the final version of his theory. In 1913, he was still developing it. So he had kind of a rough sketch version called the Endfurt version in German, which was a preliminary version that he talked about at the conference. And his idea was to replace Newtonian gravitation, which is action over a distance, with the warping of space and time. So just like if you take a piece of paper and put a massive object on it, if you take the universe and put a massive object, space-time itself becomes curved, and that predicts how other objects will move. So, for example, if you had a trampoline and you curve it, and then you put a ball, and you try to make the ball move in a straight line along the trampoline, the ball is going to travel on a curved path. Well, that's what reality is like. Anytime there's a heavy object, gravitation is the warping of space-time in that region that causes things like Earth and the other planets to move in elliptical paths rather than straight line paths. Now, going to Einstein's talk, Schrodinger became very interested in theoretical physics, and he wanted to pursue that. But unfortunately, he was drafted into the Austrian army in World War I. And at that time, Einstein was a pacifist. He did not serve in the war. He actually spoke against World War I. He continued to work on his theory. He published it in 1915. And it's a simple set of equations saying that matter tells space how to warp. Space, in turn, tells matter how to move. Schrodinger learned about the theory while he was on the trenches, literally, in World War I. And there's a picture of him at the battery in Prosecco near Trieste. Einstein made some key predictions in his paper, such that the sun bends starlight because of its gravitational presence. That can only be tested during solar eclipses. So they had to wait for a solar eclipse. There was one during World War I, but that was unsuccessful because the German astronomer who wanted to test it got arrested by the Russian army while he was trying to test the eclipse measurement, which has actually turned out to be a good thing because Einstein wasn't quite finished his theory yet and needed to revise his calculations. So by the time of 1919, Einstein's theory was tested by two teams of astronomers, one off the coast of Africa, one off the coast of South America. And the tests showed that his theory matched up much better than Newton's predictions. That if you take Newton's theory and you try to make a prediction of the bending of light. So Einstein became suddenly famous. And there were headlines. This is a New York Times headline. Lights all askew in the heavens. Men of science more or less agog over results of eclipse measurements. Einstein theory triumphs. Stars are not where they seemed or were calculated to be, but nobody need worry. Times can be very reassuring. Einstein became seen from that point on as something like a prophet. So if you look at the news from that point on, from 1919 on, people were asking Einstein questions about everything: religion, philosophy, psychic powers, you name it. They would go to him and say, do you believe in this? Do you believe in that? He wasn't seen as just a physicist. He was seen as somebody who knew something about everything. Now here's, from much later, a letter that I found at a little museum in Princeton. Dear Mr. Einstein, I'm a little girl of 6. I saw your picture in the paper. I think you ought to get a haircut so you can look better. Cordially yours, Anne G. Coxon. So people were writing to him. Children wrote to him. He was this amazing figure. He would write back to a lot of these people, too, as much as he could. So let's go back to physics. So in the 1920s, Schrodinger began to correspond with Einstein because they had published some papers in the area of general relativity, and Einstein started to recognize Schrodinger's name, even though Schrodinger was a more junior figure. And Schrodinger asked Einstein for advice, and Einstein sent Schrodinger a paper with this idea called matter waves. It was an idea by Louis de Broglie. And the idea is that electrons are not just particles, but they're kind of like these blobs that move in the atom. And somehow, by imagining these blobs undulating, kind of like plucking a guitar string, you can explain why the atom has different energy levels. You get these harmonics, like musical harmonics. And this is a brilliant idea. And Schrodinger was advised and thought it would be a good idea to work on an equation explaining how these waves move through space. And that led him to his Nobel Prize-winning Schrodinger equation, which describes how quantum waves move through space. So Schrodinger thought his equation described these matter waves, and he imagined electrons as being spread out over a region of space. Werner Heisenberg had developed an alternative theory which was very mathematical. Well, you can't have two theories of the atom without seeing if they match up. They were both perfectly legitimate theories of the atom. So somebody named Max Born, a German physicist, proved that you can describe Heisenberg's theory by lending a probabilistic interpretation to Schrodinger's theory. So Born said, hey, let's not look at these as matter waves, but rather let's look at these as probability waves. So basically, in the probabilistic interpretation of the Schrodinger equation, electrons are not spread out through space, but the chances of them being anywhere is spread out through space. So by looking at these waves, you can see, well, there's a chance the electron's here, there's a chance the electron's here, and it tells you exactly what the chances are, but you don't know exactly where the electron is. The electrons are kind of spread out in terms of our knowledge. So you never know exactly where they are. If you try to do an experiment showing exactly where the electrons are, then you lose other information about them. So from that point on, science became inexact because you can never measure the position and the speed of electrons at the same time. And that became known as Heisenberg's uncertainty principle. So Einstein was aghast by this because Einstein believed that the universe should run like clockwork. He followed a philosopher named Spinoza, and Spinoza said that nature, which he identified as God, must be perfect because it's the best that there is. So there must be some equation, Einstein thought, that would describe the whole universe for all time. And it can't be a chance equation. It has to be an exact equation. If it's a chance equation, that means that there's something wrong with it because lack of knowledge means that we're not yet doing it well enough, that science is not good enough. So Einstein thought that quantum mechanics is okay, but it's incomplete, that it needed to be completed. And that's where his expression, God does not play dice, came in. Einstein said that to Max Born, but he would say it to many other people throughout his life, that God does not play dice with the universe. So Einstein, by that time, was a professor in Berlin. Schrodinger got appointment, thanks to Einstein, as a professor in Berlin, too, so they corresponded. They both shared an interest in philosophy. Einstein leaned more towards Spinoza, and Schrodinger leaned more towards Schopenhauer. And Einstein decided at that point to take his masterpiece, to take his masterful theory of general relativity and modify it for several reasons. First of all, he felt that it was incomplete because it didn't include electricity and magnetism. He wanted to add those into the theory. He wanted a description of electrons, not just their ability to move in gravity, but also their ability to move in electric and magnetic fields. So he wanted to modify general relativity, but he also had the hope of using it to supersede quantum physics, to come up with a deterministic theory that yields the same results as quantum physics, so that he could go to people like Niels Bohr, who advocated also probabilistic quantum physics, and Heisenberg, and say, well, look, your theory is okay, but now I have a theory that's better, that predicts exactly where electrons are for all times. So he tried many methods of doing so, many ways of modifying his theory, but they all were incomplete in different ways. So the mainstream physics community had turned by that point to quantum physics and then to nuclear physics, and then to the search for new particles. So from the 30s until the 50s, Einstein kept trying new theories of everything, new unified field theories, but these were based just on two forces, electromagnetism and gravity. They were mainly to describe electrons, But other physicists came up with new particles, new forces, nuclear forces, and physics moved on. And after a while, by, for example, 1929 and the 30s, Einstein became seen as a relic by the physics community. But the press did not see him that way. To the international press, everything Einstein said and published must be great because it was Einstein. So every unified field theory that Einstein put out got a press release and headlines around the world. For example, in 1929, when he turned 50, he proposed a theory called distant parallelism, which has something to do with changing the description of parallel lines, very mathematically obscure, very hard to describe. Turned out to be completely wrong. But nevertheless, it got 11 mentions in the New York Times. So the New York Times said in January 1929, by far his most important contribution to mankind, scientifically more important than his original theory, even though it hadn't been proven yet, even though it didn't have any testable predictions. And one physicist from NYU speculated that soon people will be able to float on air using this theory. So that didn't turn out to be true. Preachers talked about his theory in churches as if it were a modification of religious ideas. So it was really a big deal. Even Will Rogers had a reaction, the cowboy humorist. This Einstein has proven a great comfort to us that always knew we didn't know much. So there was all this hype theory, but by 1931, Einstein moved on to other ideas. There was no retraction, no sense that he made a mistake in the press. Just every time he came up with another idea, there'd be headlines once more. 1933, Hitler came to power in Germany. Einstein was out of the country, fortunately. He realized he could never return to Germany. He took up a position in Princeton at the Institute for Advanced Study. So Schrodinger at that time was still in Berlin. Schrodinger could have stayed in Berlin. He had a very prestigious position there. He was encouraged to stay in Berlin. Religiously, politically, he would have been fine to stay in Berlin. But what happened was he saw that Einstein was at the Institute for Advanced Study making a huge salary, very prestigious. He had his own personal assistant recruited there. And then somebody from Oxford, Frederick Lindemann, who later became an advisor to Churchill during World War II, became a very famous figure. He went to Germany to try to recruit refugees. Schrodinger wasn't a refugee. So he went to Schrodinger and said, do you know any refugees who lost their jobs who might want a position in Oxford? And Schrodinger said, well, how much does it pay? And then Schrodinger said, can I bring along an assistant? And they said, well, all right, let's talk to the funders. OK, we'll give you this salary, and you can bring along your own assistant. So Schrodinger said, great, I want to bring along Arthur March. We're collaborating with each other. Well, that turned out to be not exactly true. Actually, Schrodinger wanted the assistant Arthur March because Arthur March was married to Hilda March. And Hilda March was Schrodinger's girlfriend at the time. So needless to say, the people at Oxford had mixed feelings about Schrodinger. There was a bit of good and a bit of bad. The good was that he won the Nobel Prize a week after he arrived at Oxford. That was good. The bad was that 9 months later, he had a daughter with his supposed assistant, who he never met with's wife. So it was a little bit embarrassing for him. So he couldn't keep the job at Oxford. They were very stuffy there. They didn't want to keep him there. He went to Princeton, lectured there, mentioned to the president of Princeton about his arrangement, and the president was kind of hesitant because he was asking to bring his wife along and also the mother of his daughter along. They were very hesitant. So he decided not to go there. And he also was reportedly worried that New Jersey might not like bigamy. And the salary wasn't as high as Einstein. So that was another reason he turned it down. So he went to nice safe, neutral country at the time, Austria, 2 years before it was annexed by Nazi Germany. So his wife Annie later said that it was a really big mistake. It turned out to be a grave mistake, the biggest mistake of his life, because 2 years later, there was the Anschluss. Austria became part of Nazi Germany. Here he was, somebody who had left Nazi Germany very prominently saying, well, I'm going to Oxford. And now Austria was part of Nazi Germany. So he didn't know what to do. So he wanted to keep his job, wanted to stay in Austria. So he decided to ask his supervisor what to do. And they said, well, just sign a memo saying that you pledge allegiance to the government. Well, Schrodinger was a great writer. He was very elaborate. So he wrote a really elaborate memo saying that he pledged his allegiance to the Fuhrer. Well, the next day that was published in the Austrian press. And then 2 days later, it was published in the international press. It was very, very embarrassing for him. And especially at Oxford, they were saying, what, this guy we recruited, we thought he was a refugee. He comes, he brings an assistant. That wasn't really his assistant. And now it turns out he's pledging himself to the Nazis. What's going on here? Well, they fired him anyway from his position in Austria because they considered him disloyal. So fortunately, he got an invitation from someone named Eamon de Valera, who was the Prime Minister of Ireland at the time. He had to leave Austria and go to Ireland. Well, some of you may have seen the movie version of The Sound of Music. Well, that was a pretty harrowing escape. But if you look at the real Von Trapp family, they actually had a less harrowing escape because George Von Trapp had an Italian visa. He had Italian heritage, so they could actually leave Austria fairly easily, and they went to the United States. But Schrodinger's escape was much more harrowing than the Von Trapp families. So what he had to do to end up in Ireland was, first of all, de Valera sent a note that was passed to 4 different people, finally got to Schrodinger's mother-in-law in her house in Vienna. Schrodinger got the note. They read it 3 times, threw it into the fire, and then they had to decide when to escape. They picked a night, and they took their car to the car wash, said, please wash our car, we'll pick it up tomorrow. They never picked it up. They had a few marks. They got on the train and took the train down to Rome, where they had to go to the Vatican since Schrodinger had an honorary appointment there to write to de Valera and accept the invitation. De Valera sent some diplomatic materials so that they can travel from Rome to Ireland. So Schrodinger was appointed to the Dublin Institute for Advanced Studies, where he became the leading figure there. And the Dublin Institute for Advanced Studies was set up to fulfill de Valera's dream for an institute where people can learn Gaelic, Irish Gaelic, but also to learn about mathematics and physics. Because de Valera was a big fan of an Irish mathematician named William Hamilton, and thought that maybe that Ireland could become a major player on the world scene in mathematics and physics. But it was really, really bad timing because they started the Institute when World War II started, and the Institute was meant to attract international support, but nobody really could come because of the war. So the Institute kind of floundered, and it was floundering, and then when the war was over, people wanted things like food, housing, but de Valera was still pumping money into this institute. So it was rather controversial. So Schrodinger had to live up to his mentor's expectations by becoming the Irish answer to Einstein. So he thought, well, all right, there are a few ways of doing this. First of all, collaborating with Einstein, because anyone who collaborates with Einstein is seen as a genius. So you see a picture here in the Irish press of Schrodinger typing a letter to Einstein. And that made news in Ireland because it was so exciting that they had, a physicist who was writing to Einstein. So Schrodinger wrote to Einstein about his theories of everything, and Schrodinger said, well, I want to develop a theory of everything too, and they corresponded, and they had a very close, warm correspondence about ideas toward a theory of everything. Then Schrodinger would go to the press and say, well, look, see what I'm doing? I'm working with Einstein and maybe even coming up with better ideas than him. So the Irish press had a lot of stories about Schrodinger. This story is the Adam Man at Home. That's Schrodinger with his daughter, Ruth, who's still alive today, living in Austria, playing chess. And every couple of weeks, they exchanged letters about theories of everything. Einstein was really delighted because Schrodinger critiqued the idea of randomness in quantum physics. So Einstein called Schrodinger his nearest brother. They developed very, very similar theories. But then Schrodinger would go to the press and brag that he had insights that Einstein lacked because he saw flaws in Einstein's theories. And Einstein wrote in April 1943 to Schrodinger that there was one type of model called a theme theory that had found a beautiful place in the graveyard of my unfulfilled hopes. It was a theory he had worked on many years before that, and basically he was saying that the theory is dead. Well, Schrodinger went to the press and said, well, actually, I've been able to work out that theory that Einstein couldn't work on, and I actually have some predictions. So he made some predictions about Earth's magnetic field. Turns out Schrodinger didn't know much about magnetism, so the predictions were off. Nevertheless, the Irish press had a big headline, Einstein had failed, and quoted from Einstein's letter that Schrodinger showed to the press that the old theory had been in the graveyard of his hopes. So Schrodinger found some limitations, decided to extend the theory in consultation with Einstein, and then January 1947 announced at the Royal Irish Academy that he had found a theory of everything that predicted the entirety of the Earth's magnetic field. And this became trumpeted in the international press, including this headline in the New York Times, scientist in Dublin claims he had achieved unified field theory sought for 30 years. And they sent letters to Einstein trying to get his reaction. Well, imagine he had been collaborating with Schrodinger, working very closely, called him his nearest brother, and then Schrodinger goes to the press and said, ha ha, I beat you to your own theory. Not very becoming of a physicist. So this is where the announcement took place in the Royal Irish Academy. And here's the equations that Schrodinger used. And then Einstein was furious, and he issued a press release scolding the press for reporting things that are not completely proven. Well, if you look at the history, the press did the same with Einstein's theories, but Einstein was really upset at the press for trumpeting Schrodinger's theories when they had little validity. And reportedly, they threatened to sue each other for plagiarism, and it almost ended their friendship. They stopped corresponding for a few years. And then by 1953, papers showed that both of their theories were wrong. And Einstein kept striving for a unified theory until the end of his days. So there's a picture here of his office the day of his death, and he was still working on unification. So we see here an example of where the media or media attention can drive a scientist towards making a report of something that is very preliminary. And it really drove Schrodinger to become, in a way, narcissistic, because Schrodinger thought that he had come up with a theory, that he'd been blessed with a theory that nobody else in the world had developed. He thought, well, Einstein came close, but he thought here he was, and he almost took it as a divine calling, that he was sent to Ireland to develop a theory that would explain everything in the universe. And he really believed that. And it was embarrassing for him, humiliating for him when his theory turned out to be wrong. But then he moved on to other things. He wrote some books on philosophy, Greek philosophy. And finally, luckily, before Einstein died, they had corresponded a bit and kind of made up right before that. Schrodinger died in 1961. So more about Einstein Schrodinger and their quest for unity is in my new book. There's a lot about Einstein's life, Schrodinger's life, their friendship, and how they fought together against quantum randomness and tried to work on a theory of everything. And scientists today are still trying to pursue a theory of everything, taking up from where Einstein left off, but this time they're trying to integrate quantum physics, which Einstein didn't like in its probabilistic form, to try to come up with a theory that includes the four known forces, including the nuclear forces, but also includes quantum theory and can explain the whole universe. And that's where we stand today. So the search for unification still goes on today. So, thank you. For questions? Okay. So we have 5 minutes in case there are any questions from the audience. Please raise your hand if you have a question. Oh, microphone. Okay.
All right, is this thing on? Hi, sir. My name is AJ. I just had a question in regards to the overall unifying theory. What's your take on Dr. Peter Higgs, and the identification of the Higgs boson and how that may apply to the unification theory?
Okay, well, Higgs's result was developed to try to explain what's now known as a standard model. So the standard model unifies 3 of the 4 forces, 2 of them very tightly, and the third one rather loosely for now. The 3 out of the 4 forces that are unified in the standard model are electromagnetism, the weak nuclear force, which explains radioactive decay, and to some extent the strong nuclear force, which is not completely understood yet. But to unify these forces, you need to imagine that all the particles lack mass in the theory, that they don't have any mass. So they're all equal, all equally weightless in the early universe. Well, then the question arose, how do particles get mass? Well, Higgs boson theory explains how particles get mass through a kind of mechanism where there is an energy field in the universe, and the energy field is rather sticky, and particles moving through the energy field mostly have trouble moving through the field. They kind of become weightier. So electrons acquire some weight, protons acquire more weight, other particles acquire even more weight. So by reacting to this energy field, its stickiness, to use a kind of metaphor, each particle acquires mass. The Higgs boson that was found was a remnant of this energy field that was found in a Large Hadron Collider, and its discovery supplied the last missing piece to the standard model. So the standard model is pretty much complete now, so scientists are now looking for evidence of new phenomena beyond the standard model, which could point perhaps to a unification with the fourth force, which is gravitation.
Sometime in the last year, it was thought that, I believe it was a large galaxy was seen in 2 different places in the sky because the light from this gravity had been distorted perhaps around a black hole, and that was demonstrating the warpage of time and space. And perhaps it was seen in two different places millions of years apart, the same object in the sky. Did you hear about that? It was got a lot of press about 8 months ago.
I didn't hear about that particular example, but that is called gravitational lensing. And when you have a massive object, and the black hole I would imagine would be a supermassive black hole, such as ones in the centers of galaxies. Well, these supermassive black holes are extremely heavy, much heavier than the sun. In fact, they would weigh as much as millions of suns. And they're so heavy that they create this great gravitational impact, and we imagine space-time being dramatically warped there. Well, if you have a galaxy in the distance and its light is coming through, its light will be split up by this warping of space-time if the galaxy happens to be in the right position. So it creates two light paths, and when we trace them back with our telescopes, we see the galaxy in two different places. We see it as a twin. And this phenomenon has been known for a number of decades for other galaxies, this gravitational lensing phenomena, and it's an excellent way of confirming Einstein's general theory of relativity.
Question. Yes, this side. Oh.
Okay, I'm
Yeah,
sorry.
That's okay. Could you comment on the progress in solving Schrodinger's equation, and how does Schrodinger's equation reflect his personal life?
Okay. So Schrodinger's equation has been solved in simple cases many times. It's done, probably students are solving it right now in second-level physics courses. You can find basic solutions very easily. Once you get up to things like uranium atom, like very complex atoms, then you need to make some approximations. Now, in terms of his personal life, I don't think the equation itself reflects it, but there is a story behind when he wrote the equation, which is that he said goodbye to his wife, met up with one of his ex-girlfriends in a resort in Switzerland, and that's where he wrote the equation. So somehow this ex-girlfriend, whose name is unknown to history, was his muse when he wrote the equation. So that's the connection, but not the equation itself.
Could you discuss, over this side now?
Okay. Sorry, the light is
lights
right in my
must be
eyes.
terrible, yeah. Could you discuss a little more the connection between quantum randomness and the Schrodinger's cat example? I mean, my understanding of the example was that it was disproving quantum randomness because it's basically saying, well, if you can't tell whether the atoms decayed, then you wouldn't be able to tell whether the cat's alive or dead, and that's really absurd. And yet it seems as if today that's understood more as, well, quantumness is just really very strange, but I think what Schrodinger was trying to do was really disprove the indeterminacy and say, I mean, if you extend the experiment and you wait before you open the box, you're going to find signs of, non-quantum decay, and that cat's going to have been dead for a long time. It's very clear that it's been dead. It's not just dying when you open the box. So why didn't it actually seem to have accomplished what Schrodinger thought it accomplished?
Well, there are a number of reasons for that. First of all, even though the Schrodinger's cat thought experiment is well known now, it wasn't very well known at the time. And secondly, he was trying to show the absurdity of indeterminacy, but also the absurdity of connecting something that's macroscopic with something that's microscopic. So I'm sorry we're out of time now, but I will be signing my book. Thank you very much.
This has been a presentation of the Library of Congress. Visit us at loc.gov.